recording.
No worries. All right. Awesome. Thanks everyone for joining. Good morning, good afternoon. Right now it's 9 p.m. here in Singapore, but for our speaker Aika, it's just around like 2 p.m. in Zurich, if I remember correctly. There was some mishaps between the time savings hour, but anyway, welcome. It is my pleasure to introduce you to our let's say lab. I'd say lab, let's say in quotation marks in a sense because it's a very unique place where all of us are happy to do research in both hubs, Singapore and ETH Zurich. So let me just briefly share 5 slides about what we do here in Singapore and in Zurich and the different sort of organization that we have and how each of the presenters will talk about their own research project as well as kind of like the research team they're part of. They're part of. So the Singapore-ETH Center or SEC, it's a place that we have more than 200 researchers. We've been in Singapore for almost 15 years now. And we primarily are a synergy between Singaporean entities as well as entities of research under the ETH umbrella in Switzerland. Here are some numbers, but pretty much it's sort of the staple, industry talk. But primarily, it's just to show you how strong these ties in between these two countries, which are very far apart, but nonetheless share a lot of similarities in terms of problems they're facing with limited land and a very small population, and a very attractive place to bring talent in to conduct high impactful research. The company, let's say, Singapore ETH Center, is comprised now primarily out of 3 what we call main research programs. And today, all of us, myself, Aika, Abraham, and Jimin, are part of what is called the Future Cities Lab Global. There are 2 more called Future Resilience Systems, Future Health Technologies, and you can go to their websites and know more about them, as well as other projects that are, let's say, not as big as an entire program, but nonetheless, they hire and have a lot of current researchers working on this years-long project. I think the smallest one is 1 year in duration versus other ones could span 2 or 3 years, maybe more sometimes. As I mentioned, it's primarily this network of entities between the ETH umbrella in Switzerland that encompasses ETH Zurich, of course, but also EPFL, EMPA, different universities around that country, the Chamber of Commerce as well, and entities here in Singapore. I did my studies in National University of Singapore, that's here in NUS. Same as Abraham is also linked with that university through this SEC. But for example, like guys is doing her PhD at ETH Zurich, but because she's part of SEC, she's still, we all work together. And despite NUS, we have other local universities working together, as well as research entities, such as A-Star, is somewhere there, the cursive A, as well as other research agencies and government agencies that are interested in having our research apply to development in the country, R&D, and potential commercialization of these things. Now, just before handing over to Aika, I just want to briefly give a shout out to another tool that our researchers unfortunately could not come to present, which is called Yourscape. The link is right there. It's an in-house tool that was developed by our researchers in urban planning and geography that is more about visualization and planning to help communities that perhaps don't have the infrastructure or technologies to just run some model directly for, I don't know, Hugging Face or whatever, but they have the intent to use technologies in their favor for planning or for other disaster relief and primarily in the global south. They work a lot with cities in Indonesia and in India. Well, that's not global south, but the point is, it's a nice tool they develop, and now looking for beta testers and more people who might be interested in it to contribute not just to development but also use cases that they might have. Think of it as like some sort of like ArcGIS meet Silcium and these kind of nice visualization tools for digital twin and digital planning. This is just another image of our colleagues. That is Joshua Vargas and Agustin Escobar showcasing this tool in our office here in Singapore. Now, without further ado, I can pass it over to Aika. She will give a very interesting talk about her PhD studies as I mentioned, kind of like dual appointed in a sense in this institution and in ETH Zurich. Aika?
Thank you, Matthias. Okay, I share my screen. I hope you're seeing it well. Today, I will focus on how we use generative models for BIPV facades. As Matthias said, it's part of Chair of Architecture and Building Systems at ETH Zurich, as well as Future Cities Lab Global. And I would like to first introduce our module. Our module has four work packages, and we try to develop a holistic approach for assessing large-scale deployment of BIPVs in urban contexts. Our researchers try to answer the questions such as how can solar energy yield be estimated realistically in urban contexts? What are the urban and system parameters that influence emissions of BIPVs? And where and when should we place BIPVs in a city? And how can we maximize the utilization of solar energy by sector coupling, specifically through electrical vehicles? And what are the localized BIPV solutions? And what are the next generation tool sets to integrate BIPVs in urban design and decision making? So we have two hubs in Zurich and Singapore. I'm part of the hub in Zurich, and today I will focus more on the first work package about the design. So first, you might ask, why BIPV facades? Because on-site energy generation is an important aspect to reduce the load on the electricity grid. And why on facades? Because we need to preserve the agricultural land and natural landscapes in certain contexts. And in the case of Singapore, for instance, the land area is limited. However, in high-density cities, facades offer large surface areas for PV application, and rooftops alone cannot meet the demand. And for these, we need a robust and automated methods that facilitate the evaluation of BIPV facades. And we address two aspects when it comes to BIPV facades. The first is there are uncertainties due to the intermittent nature of solar energy and the impacts of complex urban contexts, such as shading. And the second one is facades have complex architectural features. They contain elements like windows, doors, and balconies, and we need to take all these into consideration. First, I will focus on the prediction of urban solar irradiance. Why do we need AI for this? Because existing physics-based simulation approaches require a 3D scene of the entire urban area, and they use sky models and ray tracing simulations, which result in a deterministic annual solar irradiance sample, which are computationally intensive. To overcome these, my colleagues train deep generative network-based surrogate model, which takes fisheye images as the input, and they process it. They segment it into different components such as ground, opaque surface, glazing, and sky. And then they train autoencoders as well as GAN models to generate a stochastic ensemble of solar irradiance data. So how do they prepare the data set? They capture fisheye images with no, low, and high V0 ratio, and then they turn it into an unfolded semi-cube map. And then they generate the masks using one-hot encoding technique. And overall, they have 5,000 sensor points. And using these three categories for V0 ratio, this results in 15,000 images. And the simulations are done for 10 different cities, which represent two Köppen classification climate category. And overall, they have 75,000 images for 5 locations in these 2 climate categories, and the train to rest ratio is 4:1. So the training has 3 steps. In the first one, they use variational autoencoder. They take the ground truth image, and then reduce it into latent representation and reconstruct it. However, reconstruction is low fidelity, and for this, they train a GAN model with modifying the latent representations and generating more realistic images. And in the third step, they use doppelganger to generate a stochastic ensemble of sequential data sets. So, for instance, for a location in this 3D model, using only one fisheye image, variations of different V0 ratios, different heights, and also view angles are generated using GANs. And as you can see, these contain the stochastic nature. So there is not only one result, but multiple feature set time series data set has been generated. And this is also a sample. And the predictions and the generations are done for a week. And then these weeks are stacked. You can see the generated and the ground truth. Sometimes it captures the trends well, but sometimes it can be a little bit off. And this can be linked to the approach used to generate weeks and then stacking them due to computation limitations. But future studies will also address this issue. And when it comes to the performance, when we look at the divergence metrics, you see that for Zurich, we have a slightly better performance, which is good with the score lower than 0.1. For Singapore, we have more variations. When we look at the annual cumulative solar irradiation, the performance drops a little bit, but we are still within acceptable bounds. And if we compare the computation time, here you see the solar GANs performance. Compared to classical simulation-based approaches, it significantly reduces the time needed. However, the very first step, the rendering of fisheye image, takes slightly longer due to the method used. However, this is possible to be reduced in future studies because there are many other lower resolution as well as faster methods that can help a user to take fisheye images. Okay, so far we focused on the environment that a facade faces and the impact of this environment on the solar irradiance. If we want to look at the facade itself, what happens? Like, how can we incorporate the architectural details of the facade itself? For this, we propose a second approach, segmenting facades to generate solar potential predictions. And you may ask, why do we need AI for this? Because existing methods rely on the assumption that facades are often 50% available, or they have some other categories like only 1/4 or the full facade is available, or they rely on user input, which is manually generated, or experts take part in this. To avoid this and automate this, we use segmentation models. We first acquire images of buildings and capture some numerical and as well as some categorical data, and train a segmentation model and analyze the outputs. And we use these outputs to estimate the energy yield. So our very first data source is Federal Statistical Office of Zurich. We collect the data about the building, address, number of floors, azimuth angle, facade width are some of the information we collected. And using this information, we capture images using Google Street Views. And we try to optimize some of these parameters with analysis of the distance to the facade and the angle of pitch as well as heading. And in the end, we result in 15,000 images. However, these images are not always optimal. As you can see, sometimes images doesn't exist. Some of these images are highly obstructed by trees, cars, people, And for this, we trained an autoencoder, which helps us to quickly differentiate between images that are highly obstructed versus images that contain facades. Although the model performance is not so high, it allows us to speed up the scanning process. And then we train a segmentation model. It's a well-known pix-to-pix segmentation model from Isolam. We use the training settings they used in the original paper. We use 400 training images for 300 epochs with the batch size of 1. And we also adapt the data augmentation techniques they used. And we use patch GAN as a discriminator and UNet for the generator. And images belong to CMP facades database. This database has labeled images in 13 categories, such as cornice, blind, balcony, molding, etc. Here you see the generation loss, which is a combination of adversarial loss and L1 loss. And we trained the model with the varying batch sizes from 1 to 16. And although the higher batch sizes show a lower loss values, we still needed to have a look at the images themselves. And here in this table, there are 3 images. And if you focus on the batch size of 1, for instance, we face some artifacts and we optimally selected the batch size of 2. And using this model, first, we noticed that some of these categories may not be necessary for our analysis. That's why we merged some of the labels. And these labels in the end categorized into 3 main classes: available facade area, window area, and unavailable facade area. And then we applied this model onto 100 buildings in facades, 100 facades. And here we noticed that the mean is very close to the assumption of 50%. However, there are significant variations between different facades. And we focused more in detail to 8 facades. And by using the utilization factor, available area found by the model, we calculated the annual solar irradiation values. So here you see 3 colors. 3 colors show 3 different methods, and the dashed bars show the 50% assumption. And as you can see, the dashed bars are always higher than the solid bars, and the light colored bars are for the ground truth. Consistently, we underestimate the solar irradiation. However, in 7 out of 8 studies, the predictions from the segmented model are closer to the ground truth values. However, as we all know, pix-to-pix is a valid method, but now we are using vision transformers, diffusion models, and we are also trying to implement these approaches. Here you see an implementation of segment anything, and we are also trying to turn it into a tool. We take into account the facade area, the orientation, the PV technology, and the location. And by using a PVGIS API as well as segment anything API, we are evaluating the available facade area for PV application and then predicting the annual energy yield. And this method can be can help us to upscale the approach we developed, and also can be used for different facade images in different contexts, and it will be available soon. And overall, in the context of BIPVs and facades, we use AI to overcome the computational demand of simulations and consider uncertainty due to the intermittent nature of solar energy, and generate more accurate estimation of surface utilization factors by considering architectural details. And please feel free to scan these QR codes to read more about our work on powering the city module. And if you're interested in details, feel free to reach out to me and my colleagues, and I look forward to the discussion.
So thank you, Aika. The next presenter will be
Abraham.
Abraham.
I'm
Okay.
here.
Okay, thanks. Abraham, can you share your screen?
No problem. Give me a moment. Sorry. Okay. Thank you, thank you very much for the introduction. And just to introduce about our project. So I come from the project called the CCAI interface. Our project is also very similar to what the other FCL projects about, but it's a more design-focused project. So right now you're looking at our website that we have two branches. One is on research, where I'll be talking about today. And the other aspect of our project is the design aspect. So every year for the past 2 to 3 years, we host this kind of competition where schools around the world will submit the idea of what a C-City interface means. So the idea of C-City interface is that as we experience climate change, there could be sea level rise is going to be the norm in the future, and how can cities, especially coastal cities, respond to this kind of sea level rise, both in terms of research, in terms of practical adaptation, or in terms of planning and architecture, and how can architecture respond to this. So feel free to search us up, just called the C-City interface, and to take a look at our results, research and also competition results. Now I'm going to share my work. Right. So let's go back to that. So that was the CCAI interface. About myself, my name is Abraham, and I generally work on using AI for data purposes to enhance the data accessibility of our work in the project. So I'm not sure about you. There's been if you have ever done a research that is global scale, one thing that always sort of restricted me and our research is the availability of data, whether you are able to get data for a very large area in terms of climate data, for example, or urban data, or you might want to get a very high resolution, 2 meters, 5 meters, 10 meters resolution for a smaller area. It's probably easier in North America and Europe, but it's not as easy as you would here in this part of the world in Southeast Asia. So this research is one of the first research that I personally encountered a problem. So this is where we try to map the solar panels and also green roofs of cities around the world. So you can see that we were trying to use a convolutional neural network to identify whether there are solar panels and also green roofs on buildings for many cities in the world. So you can identify that these cities are North American cities. We also try to include some other cities, including Singapore, where we're from. But the problem is that even though the results were quite good for most of the cities in North America and Europe, we had to drop Singapore from the research. The reason is that when it comes to our part of the world, the open access data for satellite images, those freely open to researchers, are very limited in resolution. And even with a human eye, you can't really figure out what is a solar panel, what is a green roof. So it's really ironic because when we reported our research, so a research group from University of Singapore couldn't actually get good data for our city, whereas we can actually get data for other cities. So with projects like this, CCD interface being global, this is one of the biggest challenge that we have. So I was really frustrated, right? So like, how can we make this better, especially we're here in Singapore, we have to study about Southeast Asia. So I look at this issue a bit closely. So the idea is that, well, at least in the open access data world, you always have different data qualities, right, between different data layers. Whether you're working with raster images like satellite images, this is from OpenStreetMap, whether you're working with vector data. So here's the example, right? You see that the satellite image here is very blurry. I just took a screenshot from the interface. And whereas the same place, right, has a lot of data in terms of vector data. So you have roads and buildings and point of interest clearly labeled as vector data. And when you go to Seattle, the situation is flipped, right? So you have very high resolution satellite images here, but you don't really, I mean, you only have streets and some blocks in terms of the vector data. So there's always this kind of discrepancy, especially when you're looking at an open source platform. So this kind of pattern basically repeats all around the world between different cities, right? In some cities, in Seattle, for example, you could have very good access satellite data, but in Singapore, you don't really have it. Some cities are even worse. So this is example from Shenzhen, where you have blurry satellite data and you don't really have a lot of vector information, but you also have the best of the best, right? You have Berlin, in this case, very good quality data for all data layers. So obviously, the research done in North American and European cities are much more, I would say, efficient and accurate. But there's something that we can probably do with this, right? Because we do see an opportunity here. So because you see, if you look at these images closely, you see that most of them are very correlated, right? So with some data that is labeled in the vector space, maybe I can use this data to enhance my satellite image or vice versa. So this is something that we were trying to do in my research across different data sets. So, one of the first example that we tried is that, well, let's do a simple one first. So if you look at, so let's do a vector to vector data translation. Let's say that we know that street networks are highly correlated to building morphology. And we also know that, at least in OpenStreetMap, building networks street networks are generally 100% complete for the entire world, whereas building polygons that you see here to the right are only about 60 to 70% complete. So what if you can do that and you can train a model, which in this case, again, to generate the building footprints to the right. So it turns out that if you input the correct parameters, you can actually do so, right? Here I prepared some generated versus real images. You can see that as long as this would provide the street network context, it could actually behave pretty well. And if you apply this model across different cities, you can see that in most of the examples, you can actually reproduce urban morphology quite well. But what is the use? What is the use of this, right? So the next question we want to ask is that, can we make it a little bit better? How can we make it useful? That is here, in the sense that something that the CCAI interface is very troubled by, which is the availability of DEM data in our region of the world. So DEM, digital elevation models, can be used to do flood modeling, right? So without a very high resolution DEM, you can only do a very generic flood modeling without hitting the right places. And one of the biggest problem in DEM that is globally available at 30 meters, like the example you see here, these are generally collected by satellites that are not recent. For example, this data set I was looking at, it's from the year 2015. And in this part of Asia, where development, just happens every 1 month, you could have very different data when you collected data in 2015 versus today. So you can see here, compared to traditional super resolution, you can actually not just enhance the resolution of the DEMs, you can also input the missing information that is in this DEM. But yet again, we're still using a GAN model behind it. You can actually use any kind of generative model. The idea is that for the input of the generative model, you want to use a multi-layered input. So on one hand, you want to put in the 30 minutes DM that is here. That captures the kind of height, kind of minimum elevation and the maximum elevation and the relationship between them. And also some of the additional context, right? So in this case, it could be, yet again, street networks and building polygons or other related spatial markers that helps the model to learn. And then obviously, you also need to have a ground truth, right? And fortunately for us, many of North American cities, the USGS has very good access, 1 meters DM resolution that is LiDAR derived. So you can actually train the model, right, to convert this image to that. Then we would have to measure how accurate that is so that we can use this model in our region of the world. So if you do some benchmarking, we realize that this is actually very good. This one, where my cursor is the result from our data. Right, so from 30 minutes DM, right, if you put it into the model, you actually get this. What you get is the kind of, you can actually see the street network and the building polygons delineating these kind of borders, which are very important when you do urban scale flooding, because when you do an urban surface runoff, you don't want to, the water should run away into the streets, not into the buildings. So compared to some of the bicubic upsampling, or even compared to a vanilla GAN, like a cycle GAN, you just generate the model. It is actually performing much better. And if you look at the errors as well, right? So I'm comparing a vanilla cycle GAN which is just the input into the model versus if you encode with the context, you can actually have a much better image in terms of fidelity, a much lower error. So we can do that. We can do this for multiple cities. We can do a very large model by training hundreds of thousands of images across cities. And here are the results. So these cities, Vancouver, Denver, Pittsburgh, Zurich, these are cities with ground truth data, with a lot of ground truth data. So we can train them, train the model on, and also verify the model. But that's not all, right? Because that is really just in theory. The whole point of this exercise is that if you can actually create a model that is trained on other cities with high resolution data, and you can want to apply that to a region like Singapore where there is no access to such data. So obviously, in the best situation, you want to be able to fine tune a little bit, right? Because whatever that is, whatever the geography or the urban morphology in North America might not be wholly applicable to Singapore. So you want to fine tune it, and after that, you can apply it to a much larger area for inference. So if you look at this image, this is what I was trying to say, like we have trained a large model about 300,000 images for North American cities. And if you just apply it to Singapore, it might not make sense. So after begging our local agency, we were able to secure this stretch of data with high resolution 2 meters DM. So then we can use this ground truth to fine tune the model and also verify how accurate that model is. And so this is the end result. So you can see that compared to what we have previously, you can actually create a high resolution DM for the entire region. And so you also want to compare, how does this work, in terms of the fidelity. So now we have a slope analysis where you can see that how that 30 minutes DM, yeah, gives you some kind of idea, but how that ground truth gives you the full picture, and how the fine-tuned model here has the best fidelity, right, compared to the ground truth. So this really opens up a lot of potential use cases. So here's the detail, right? So if you zoom into the same area in parts of Singapore, the 30 meters DM versus the 2 meters DM, this 2 meters DM contains a lot more information, right, for us to use for any downstream processes. So why is this important, right? So we can use, so for the first time, we can have access to high resolution images at a very low cost so that we can actually conduct a lot of flood-driven research. So this research will continue to be pushed forward, and the next year we'll have additional results on this line of work. Lastly, I just want to touch on this one. So the idea of using kind of GANs or generative models to enhance data, right, to extrapolate data, it doesn't really stop from enhancing the DM image or just plotting out building polygons. So this animation that you see here is what we're trying to do to use GANs to do flooding directly, to use flood modeling directly. Now, in the past, I mean, even nowadays, the standard practice is to have a DM image, right, digital elevation model, and run a lot of computational intensive modeling on top of that DM. So, well, those who are flood modelers will know that there are many algorithms to help us to get to the best possible accuracy. But this is like a classical algorithm in the sense that it requires a lot of expert tuning. There's a lot of domain knowledge required, and it is all simulated. So we were trying to look at, okay, so actually we have a lot of flood database, right? So one of the most kind of famous database for those who are in the US would know that it's called the FEMA National Hazard Layer. So for the entire contiguous United States, the FEMA, which is a government agency, publishes these maps. So these are the blue ones here. Publishes these maps in many counties. And as long as your building sits within these flood zones, you will know that the government will tell you, and then you will have to be insured against flood risk, which helps a lot of communities. But if you just look at here, you see that there are many regions that are not mapped. Generally well, we're not sure about the reason why. The study is still in progress, but the idea is that there are many regions like this place, right? The flood map just cuts off. And here you would think that the flood map would just continue to go into this county, but it's just cut off. So with the same idea, right, with the same methodology and the same package that we've created, you can actually now train the model on the lighter blue flood zones, and the model is able to extrapolate the darker blue ones, which is the generated flood regions. So now, without going to a professional risk engineer, at least from a FEMA mapping point of view, we can actually do it quite well using an AI by just learning what FEMA has done for the past 40 years and trying to fit it up. There are some metrics here in terms of precision and recall. So the idea is that we want to overlay the predicted and the generated the generated flood areas, and also with the ground truth flood areas to see how accurate that is. You can see one on the left, which is the generated, another one on the right, which is the ground truth. They're pretty close. And so the significance of this is not just theoretical and say, oh, wow, you can really reproduce it really closely. The idea is that there's a lot of newspaper reports saying that my city is actually being flooded every single year, but there's no FEMA maps. So we cannot get our flood insurance, or when the flood insurers come, they just charge us a very high price, right? We find it unfair. So this is a city in Michigan. But you see that the lighter blue areas are the FEMA flooded zones. So you see that the majority of the city is to the east, right? And this tells you that the city is pretty good, right? There's no flooding. But actually, this is what is supposed to be according to our model. So all the blue areas here are, well, with this, you will be able to count the number of areas and also the population that are impacted. So in Michigan alone, right, in the state of Michigan, FEMA maps about 135,000 buildings, and which is with the lighter blue area. And once we ran on a model, we realized that for these redder regions, which are unmapped by FEMA, these can go up to 130,000, which is about 100% increase in that. So nationally, if you plot this, you can see that the The redder legend is about the FEMA mapped. So whatever that you see here are already being mapped by FEMA. So they actually have done a pretty good job, given that it's a big country. But the example that I show in Michigan here, and also some areas here, right here, and you can see that there's a huge discrepancy in the areas that FEMA has mapped versus where they're supposed to be mapping. So the idea of this research is not to say that FEMA didn't do a good job. In fact, that we want to say that FEMA has done a very good job, in the sense that mapping of very highly dense areas. But there are many other areas that are generally more vulnerable in terms of this building construction, in terms of its flood risk, right? That have not been mapped. So this work is still a work in progress. We wish that more data will come out of this, so that we can understand how we can better help FEMA to complete this map, so that everyone can have access to flood insurance. So this is really this is everything about our research, and I'm happy to connect and happy to answer any questions that you have. Thank you.
So thanks, Abraham. So the next speaker would be Qiming. So Qiming, if you are ready, you can share your screen. Thank you.
Can you see my screen now?
Yes.
Yeah, thanks a lot to Ivan and also Matthias for your invitation and organization. And also thanks to the previous two presenters for their wonderful research. Hello everyone, and good evening and good afternoon. I'm Qiming, and currently I'm a postdoc and also the coordinator for the Adaptive Mobility Infrastructure and Land Use module in FCO. And my sharing topic is reinforcement learning for sequential planning decisions under uncertainty, a case of planning charging infrastructure over multiple years, which is based on most recent research article that we have just submitted and is currently under review.
Jimmy, sorry, maybe you can swap screens. I think we're watching the presenter's view.
Oh, really?
Yeah.
Okay. Here, let's full
Yes.
slide.
Yes.
Okay.
Thank you.
Yeah. So basically, there are three major trends in the transportation area. The first one is automated transport. The second is shared mobility, and the third one is the electrified transportation. And currently, so there are a lot of studies dedicated to the electrified transportation, which shows that the electrification trends may contribute to reduce half of the CO2 emissions of the total emission from this sector, and also combined with the shared mobility like ride sharing, ride hailing, the demand responsive transport and robotaxis, such effect would be amplified. So however, there are several obstacles facing the massive deployment of electric vehicles. The first one is the battery capacity, which plays as the predominant factor that contributes to the range anxiety of EV drivers. And the second one is energy transmission efficiency, which relates to how the electricity or the power being transmitted from the generators to the grid and then from the grid to the battery. And lastly is what we are concerned here in the research or in the domain is the access to charging facilities, which relates to the infrastructure planning and operation. Actually, the surging demand for example, in China, as the major EV adoption market, there are 20 million gap in terms of chargers deployment. And the annual increase rate compared with the last year was 27% in terms of deploying new chargers. And particularly in Singapore, the Singapore government set a goal of deploying 60,000 charging points by 2030, which would be 20 folds of the current figure, which is like 3,000 at the moment. In terms of the publicly accessible fast chargers, actually the publicly accessible fast chargers are aimed at serving the, for example, the e-taxis, the buses, and also part of the private EVs in the future. However, that also represents a great gap in Singapore, but also it is a quite normal phenomenon for other countries around the world. So there is a huge gap in deploying such publicly accessible fast chargers. So when we take a close look at the charging technologies, currently there are three major charging technologies being studied and being practiced worldwide. The first one is the slow chargers, which is also known as the AC type charging technology, which belongs to the plug-in charging technology as well. And above that is the fast charging technology. And lately, you may heard of something like the ultra fast charging technology. So these previous three types of charging technologies belongs to the plug-in charging technologies. Beyond these types, there are wireless charging. So inside wireless charging, there are several subclasses like dynamic wireless charging, quasi-dynamic wireless charging, and static wireless charging. And after that, we have the battery swapping and also the discharging. Discharging means the vehicle to grid technology. As I have mentioned, the deployment of publicly fast charging infrastructure compensates for the lack of access to home chargers in densely populated cities like Singapore, like London, like New York. For example, in London, like 40% of the vehicles have to park on the public street overnight instead of being parked at privately owned garages or parking slots. So that also supports the government's goal for rapid EV deployment and also the commitment to the carbon emissions globally. And another concern is that massive deployment of EV should integrate with the constraints of the power network. I assume that some of you are experts from this area. For example, the massive deployment of EVs may cause the power fluctuations during the peak hours. And secondly, deploying the chargers also have to consider the readiness of the power grid. You cannot randomly deploy like 200 fast chargers or even chargers at a place where the grid network cannot support that. Thirdly is the configuration of the renewable distributions and the renewable energies, how we could maximize the utilization of these types of energies and to support the massive deployment of EVs is another hot topic in this area. And finally, is the V2G technologies. Prior to this project, we have published a review article which reviews 2077 models that try to plan or optimize the location, size, and types of chargers to support the EV adoption. And later on, we dive into the concrete research gaps in deploying fast chargers for shared electric vehicles. So there are three major gaps. Firstly, predominantly the one-off optimization approaches or the deterministic optimization methods are widely adopted. So basically, they ignore the temporal dimension of planning. And secondly, their yearly travel demands or ride-hailing demands and the shared electric vehicle fleet size were statically modeled, neglecting, the stochasticity nature of how these patterns change over time. Thirdly, is the charging demands were oversimplified in terms of how they distribute in space and time of the working days or even at weekends. We have defined a problem that we try to focus on this conceptual model is that we try to determine the timing, the location, and also the capacity of fast charging stations for deployment within extended planning horizon, for example, several years, and under uncertain factors. And the uncertain factors that we account for includes the ride-hailing demand increase, the fleet size fluctuations, which were decisions made by the TNCs, for example, Ubers, Grab, and also the stochasticity in daily charging demand distribution. And the objective actually we consider here comprises two parts. The first part is the charging service efficiency, which was highlighted in the green box. Second is the minimum number of fast chargers over the planning horizon, which is highlighted in the blue box. And we propose this reinforcement learning planning framework so that we could accumulate the reward or the goodness or fitness of our plan within multiple years. So here you can see in the objective function, the gamma represents the yearly discount coefficient, which is a hyperparameter, which accounts for like the closeness of the fitness of the value of the plan. For example, if we are considering the plan of the current year, then gamma could be 1. If we are considering the scores that could be obtained in the future years, then the gamma could be like 0.5. So it is discounted. And then the first objective refers to the charging service efficiency, which is a weight of the net charging time in all time spent, for example, which includes the charging time and also the waiting for queuing for charging time spending. The second term of the objective represents the number of chargers left for future deployment at a station, which means that we try to minimize the required chargers to be operational at the current year. And this slide shows how we frame this planning framework using reinforcement learning. So it incorporates two modules. First is the agent-based simulation module, and it actually captures the dynamics of shared electric vehicles, travel patterns, ride-hailing, the distributions, the ride-hailing demand, dispatching, charging, all kinds of activities in the city, and also very importantly is their interactions with charging stations. So this agent-based simulation platform serves as an AI gym environment, letting the reinforcement learning module to interact with. So the other module which I have mentioned is the reinforcement learning module. In this case particularly, we adopted the deep deterministic policy gradient algorithm because of it is model-free, and also because it is we are facing with a sample inefficient condition, so that we would like to exploit the already obtained sample data and played it around to train the neural networks to attain higher performances in the action policy. Yeah, so that is like the technical side of this framework. And yes, this animation shows how we try to converge the daily EV and charging stations activities, and how to combine them together and to get a cumulative reward using the objective function. And while training the neural networks of the reinforcement learning, we try to improve the policy making and the actions which reflects the number of chargers and type of chargers made at each location could be better than the previous iteration. So in terms of the experiment that we conducted, so as I have introduced, it is a conceptual model. So a lot of assumptions sounds a little bit can be improved in the future. So we have divided the main island of Singapore into 900 plus hexagons, and we plan the fast chargers within 5 years horizon, but it can be extended further. And we use the taxi data acquired from the LTA of Singapore, and we applied 50% of the taxi trips and try to randomly generate some stochasticity in its growing pattern. And the initial SEV fleet is 350, and it also corresponds to the changes of the taxi trips and the ride-hailing demand. And also there are some parameters with regards to the fast chargers, and also the battery size of the vehicles. And in terms of training the neural networks of reinforcement learning, we train it in 200 epochs. However, it can be improved, but we think that preliminarily the results have already signaled the convergence. So we just train it in 200 epochs. So some results. First, we find that less fast chargers, after we train these neural networks like the model, less fast chargers were deployed annually and compared with the early training phase. And it indicates that the model has effectively reduced the number of fast chargers required to meet the two objectives we set, pursuing a more sustained growth over aggressive short-term deployment strategy. And thirdly, the generally decreasing gap between the training epoch of the last 50 epochs signals the training convergence. So you may see on figure B that while the training epochs approaches to the end, the curves, like the patterns of the deployment decisions, which represents the policy, the action policy, just try to converge and looks more and more identical. And second, as charging demand grows yearly, the supply of fast chargers scales accordingly. So that further incurred the shared electric vehicle charging demands by 20 to 22 requests per station, following the infrastructure demand reinforcement loop, which means that if we are deploying more chargers at location, then more EV-based trips will be incurred. and that will somehow resulted in more EV charging behaviors at these locations. So in figure A, you can see that if we do not include such reinforced loop, then the pattern would look like the dashed line in black. However, in our model, we consider this pattern, this type of characteristics. So there is like incurred demand, which shows the pattern just above and grow exponentially, like drastically above the dashed black lines. In the end, only around 60 chargers are needed in the 5th year, which reduced drastically from the first training epoch. And also through the optimization, we have increased the charging service time per charger by 101 seconds. However, this is at a cost of, at a slight cost of prolonged waiting time, but is still at the acceptable range. So in total, the island-wise number of chargers has been reduced by 21,000. And the last slides of the results just show the convergence pattern of the reinforcement learning model. The left-hand side shows how the total reward has converged eventually. But actually, it's not that looks that perfect, because I assume that if we conducted more training epochs, I think the curves may look more flattened. And however, it already shows some like signals of convergence, so we just stop training this model. And on the right-hand side, we just demonstrate the convergence patterns of these two sub-objective functions. So beyond this project, actually, because we are like exchange our experiences in using AI, right? And in my study, so we are looking at the reinforcement learning. So I would also like to mention something very interesting in one of our previous projects. So in one of our previous projects, we also deployed reinforcement learning. However, we further tested different training strategies. So we may facing a lot of like we may have one agent, and this agent may make different decisions, and the decisions may be applied to different locations or different cases. So we may call it like a centrally learned strategy or centralized controlled TDPG. On the other hand, we may devise a lot of decentralized training strategies, like at each location or each case, we have an agent, and the agent will train their own neural networks, have their own experience replay, and also have their like own samples to be learned off polysilly. So in the second fashion, it may be called like multi-agent DDPG. So in the previous case, we'll show that you can see that different training strategies or how we devise differently of these neural networks or the reinforcement learning model can yield distinctive patterns of convergence and also the results. In this case, specifically, the multi-agent DDPG outperforms the centrally trained one. So it's just like a very interesting point to share. Okay, so that's the end of of our project. We may zoom out a little bit to look at our team. So our team is called Adaptive Mobility Infrastructure and Land Use. We have two PIs, one from ETH, Brian Eddy. One is a Presidential Assistant Professor, Patrick Bansal. And we have three co-Is, Kayak Sawson, Peter, and Tanvi, and three postdocs and 4 PhDs working on this project. And here's a QR code which will lead you to our website. And basically, we are focusing on three pillars. In pillar one, we try to address the travel behaviors, like to understand the travel patterns of Singapore and Zurich. Specific topics, for example, includes the work from home schemes and the travel mode shifts before and after COVID. The second is social travel behaviors among friends. Thirdly is we have developed data fusion techniques, which combines the traditional house travel survey data with smartphone data to augment the power of transport data to be used for planning. Second pillar is the agent-based surrogate models. So we improve the modeling techniques, including the reinforcement learning models that I have introduced, and also other planning techniques that could be integrated with the transportation simulation platforms or models. And the third pillar is the nature of planning. So Professor Addy from ETH side, he and his team looks into the planning processes, like how we could make the multi-phase planning more sustainable and responsive. And there are several case studies under this pillar. For example, the metro line growth in Lausanne, in Zurich, and transition to a car light future in Singapore, and also the adaptive planning fast charging infrastructures which I have previously introduced. And I think this is the last slide. Lastly, is the tools. So I have introduced, basically we have developed the data processing tools, which combines the transport data, and then we develop the MatSim model, as well as like the Sumo model, which is, the previous one is more like a macro and mesoscopic, and Sumo model, which is microscopic transport model. So based on the data we fused and the MatSim or Sumo model we created, we can replicate or predict the future travel patterns for any cities. And then we have designed the AI-based planning tools, which help us to optimize our planning decisions. And based on that, we could combine those tools and platforms and AI tools together to help the transportation planners to make better decisions and also consider the different types of uncertainties in the course of planning that they may encounter in the future. Okay, thank you.
Yeah, thank you very much for the three speakers' presentations. For different topics, BIPV, flooding, and EV charging. So now before splitting into breakout rooms, I just wish to ask if there's any questions that you would like to ask the three speakers here. So feel free to ask any questions. Okay, Maria. Yes, Maria. Yeah, Maria Karina right? So you can unmute yourself. Maybe she has some technical problems. Is there any other questions from the floor? Yeah. So, I mean, all the three projects are quite applicational. So we have a co-host Miguel here. How do you find the talk, Miguel?
So I find, yes, those topics quite interesting, and the fact that they try to address different issues, and especially the use of artificial intelligence for different climate related disasters. So especially I would be curious to know a bit more in which regard the methods they use are more